So let's go for the last but not least talk of the day. It's Tim Blazytko on unveiling secrets and binaries using code detection strategies. Let's give him a warm welcome.
Can you hear me? Okay, thanks a lot, guys. And thanks, Mo. Yeah, hi. It's good to be back. Test. So thanks for the introduction. Thanks for the warm welcome. Hi, and it's good to be back. So I'm Tim. I already gave a talk on code obfuscation last year together with Mo. Today I'm back, not exactly with code obfuscation, more about something I use in daily reverse engineering, which helps me to pinpoint obfuscated code, but also all other interesting code constructs. And today I would like to talk about a little bit about that, because I think it might be interesting for you, for the one or other, to help you in your daily reverse engineering routines. Some words about me. I'm the co-founder and chief scientist of Mproof, a company based in Netherlands and Germany, where we build embedded obfuscation via binary rewriting for embedded devices. And besides that, I also give trainings on code obfuscation and deobfuscation and reverse engineering. So today, I would like to talk about something which started some years back then. So some years ago, I used to look a lot at commercial applications, especially the obfuscation. And I had the problem with how can I find the obfuscation inside large binaries, because usually you don't protect everything, you only protect 1 to 5% in larger applications. So, and I was looking for some ways to be efficient that I can, no matter the binary size, know where I should look first. So, and I come up over the years with different strategies for that. And as it turned out, they are not only useful for detecting obfuscated code. So what's the main point of obfuscated code? To increase the complexity, to make a function or to make code complex, or let it look in a way that it's really uncommon. And it turns out it basically behaves the same way as normal unprotected code, which is quite complex, like large state machines for file parsing or network protocol dispatching, cryptographic routines, and so on and so on. As it turns out, they do have the same characteristics. And therefore, I would like to talk today about a few of these things that might help you in your own. So let us start with an analysis scenario, no matter of your background, where you start with a large binary. Also, what large means depends on the context. It might be 2 MB, it might be 20 MB, or 200 MB. So what you typically do is you open it in your disassembler of choice, like IDA, Ghidra, or Binja, and then you start looking for whatever you are interested in. However, sometimes you don't know how to proceed. So sometimes you are happy if you have some context. So for instance, you are interested in locating complex state machines and protocol logic. Things you are interested in that might be vulnerable or fuzzing targets. Or think about you want to check if there's any crypto inside. So maybe in the malware context. Or what about discovering C&C server communication or in general network communication? And also, what about pinpointing obfuscated code in commercial applications, where I come from mainly, so software piracy. And of course, in the context of embedded devices especially, API functions, detection of API functions in statically linked libraries. So what you usually have there is that you have a lot of functions which are combined with user code. And if you open the binary, you are interested in finding out what's user code, what is library code. And something like that, as you will see later on, will help you also to identify at least some of the most common API functions. So no matter what you do, no matter what the context is, your goal is usually to identify interesting code locations. So where do you start? Well, the best approach is, of course, if you have function symbols. Then you can get a lot of context. For instance, if you find something like validate serial and you are into software piracy, this might be worth a closer look. However, you often don't have symbols, of course. So what else can you do? You can look for interesting strings, like is there anything which is a hard-coded server, for instance, which might be interesting in the context of malware? Or are there some serial numbers hard-coded, or whatsoever? And then, of course, also interesting API functions, like is there a string copy inside, where is the malloc, where is free, or also about if you see something like that, like get async keyboard state, which in the context of malware on Windows is usually some kind of keylogging behavior. So these are the points you are first interested in. What you then do is you start looking at cross-references. Where are these imports, or where are these strings used, and in which context, and stuff like that. However, there are lots of analysis scenarios where you don't have any meaningful API functions, imports, or strings. So in other words, these methods are not always applicable. And there comes into the game where we can look at some code detection heuristics. So the idea in general is to identify interesting code constructs. What does it mean? Well, the idea is that you get some insights, especially if you are early in your reverse engineering journey and start with an unknown binary. You want to have some insights which might be worth a closer look. So in other words, you will not find anything which solves all your problems. This is not how it works. However, your goal is to get some guidance, what might be interesting to look first, and distinguish also the false positives then. So, and especially for me, I'm working often cross-architecture. I do a lot of x86, but also do ARM, sometimes PowerPC, and so on. And for me, it's important that it works on all kinds of architectures, that I don't have to build heuristics or code which are targeting for specific architecture, and then I have to reinvent the wheel for all the others. So instead, what I'm trying to do is that the things that I build work on all architectures which are supported by my tool of choice. So, and also, these heuristics should be efficient to compute. So let's say I have a binary with 80 MB or something like that, with about 100K functions. Then I don't want to wait 5 days until I get some results. Instead, it just should take some seconds or minutes in the worst case. So it should be really efficient. So question is, how can we realize that? So in general, I define interesting code as 3 different things. First, I say interesting is everything which is potentially complex, no matter if it's complex due to real complexity or artificially complex due to obfuscation. So if code is not complex, it might be interesting if it's frequently executed. Like if there are a lot of functions which call a specific code location, it might be worth a closer look what's going on there. Perhaps it's some interesting API function. Perhaps it is some string decryption routine or whatsoever. And finally, there's something which is known uncommon. So we have a lot of typical code constructs, like function calls, like function prologues, function epilogues, and stuff like that. However, we are also interested in finding what is uncommon, what does not look like all the other functions in the binary. So we can do a few things here. We can look at some complexity things, like the number of basic blocks, or the basic block sizes, or the function size in general. So this would be interesting for complex code. We can look at specific control flow graph characteristics, like are there any loops in there? Are there nested loops in there? Or are there some kind of state machines? So in other words, we can pinpoint underlying code constructs. And of course, we can also do a frequency analysis, something like which is called often, which is common, which is uncommon. So basically, we can use that to detect common or uncommon code patterns. And in these cases, where we have to rely on some mnemonics or some architecture-specific things, we can make use of intermediate representations instead of the assembly code to get at least something that it works all across different architectures. So, in other words, we have 5 different heuristics, which we will take a look at in the next minutes. So, it's important to say that the heuristics are relative to all functions in the binary. So, it's often the case that you are not interested in absolute values. Like, this graph has a complexity of n, and if n is larger a specific value or smaller a specific value, then you don't look at that. This is not how it works. So instead, what you do is you have sometimes a series of functions which are more complex and a series of functions which are not so complex. So, and what you want to do is you want to compare them to each other and sort them relative to each other by the same metric. And then you can start seeing some boundaries, like, oh, the top 5% or the top 5 functions look really interesting. And afterward, I see a small fall down or decrease in numbers. So we will see a few examples like that in some minutes. So it's important that we compare functions relative to other functions in the binary. And therefore, we get a clear separation between functions. Second, we have different heuristics, and each heuristic detects different patterns. So there might be some overlaps in between, but on the other hand, it doesn't make much sense to have 5 heuristics if they all pinpoint the same code. So therefore, we have something that we target differently. So, and therefore the goal is also to teach you what works when and what doesn't work when. So now I would start with the first characteristic, the large basic blocks. So intuitively, we're looking functions that look like that, where we have some basic block which is arbitrarily large. So the idea there is that typical, a basic block is about 5 to 7, sometimes 8, depending on the code base. Now let's say 8 instructions per basic block on average. However, there are basic blocks which conclude 100 instructions or even 1K instructions. There are sometimes even basic blocks which have 50K instructions. So, and if you are having something like that, then it typically indicates some kind of complex straight-line code. So what this means, we will see in 1 minute. So let's see, we want to detect complex straight-line code. What we can easily compute then is we just count the number of instructions in the functions and divide it by the number of basic blocks in the functions. And this way, we get a score for the function that tells you the average size of the basic blocks per function. And then, if you start sorting the function with that, you have the top n%, which are probably the most interesting to look at. So, complex straight-line code usually can mean a few things. So, it can be unrolled loops, like a compiler optimization, which has a for loop, which is taken n times, and the compiler decides, hey, I can eliminate the branch and just put everything into one basic block. This happens, for instance, typically in cryptographic implementations. However, nevertheless, if we have unrolled loops or not, cryptographic implementations usually tend to have large basic blocks due to especially symmetric crypto, especially if you have some round-based implementations like AES or DAS or something like that. A typical other scenario where we have lots of straight-line code are data structure initialization routines, where you have complex structures or complex algorithms that have to be initialized somehow. And of course, then you have also arithmetic obfuscation, which takes simple formulas and makes them arbitrarily complex. So let us take a small example. We have an anti-cheat. The anti-cheat usually has a goal to detect cheating attempts. And since cheating in online gaming is a thing with a lot of money inside, anti-cheats try to detect cheating approaches. And since cheaters are interested in preventing anti-cheats from detecting their cheating attempts, what anti-cheats usually do is that they heavily obfuscate parts of their code. So, and if we apply this heuristic to an anti-cheat, the large basic block heuristics, we will find some instructions where you can see that one function has an average basic block size of about 1.5K. The second most complex is about 200, and then it rapidly decreases just about 40 to 60. So, and if I now start manually analyzing these functions, I find quite some which all belong to the same data structure, to the same kind of obfuscation. Namely, they all apply arithmetic and virtualization-based obfuscation. And funnily enough, the largest function on top of there seems to be an initialization routine for the obfuscator. So let's take another example, the Windows kernel. If we apply the same thing for the Windows kernel, and these are the top 5 or 6 functions, 4 or 3 of them implement some initialization routines for some data structures. And one of them implements an algorithm, a cryptographic algorithm. So, as expected, the results, this might be quite interesting to look at. Let's take another example. Up until now, we had the complexity of individual basic blocks. Let's now go to the function level. So we all want to analyze functions like that, I guess. So what you have typically here is a complex function, which means it implements some kind of complex dispatching logic, probably. So in other words, we are looking for functions with large or really large control flow graphs. So large control flow graphs often indicate a complex code logic. This might be, for example, file parsing or dispatching routines, network protocols, but also code obfuscation. And there is one very efficient metric to compute this, which is known as cyclomatic complexity. Cyclomatic complexity usually works by taking the number of edges in the graph minus the number of basic blocks plus 2. So in other words, if we have a graph like that, where we have 4 basic blocks and 4 edges, we can compute 4 minus 4 plus 2, which equals 2. So in other words, cyclomatic complexity can be understood as the number of independent paths from the start to the end. So in this case, we have 2 independent paths, namely A, B, D, and A, C, D. So what does this detect? So let us take an example. Let us first have a look at the Windows kernel. If we look at the Windows kernel, we again see that we have quite some separation between the functions. We have 3 functions, which are very complex, and then we start just having some hundreds instead of some thousands. So that's about basically the number of edges, more or less, in the graph. So, and if we start analyzing these functions, it turns out that the first 3 belong to something which is known as patchguard. Patchguard is the anti-tamper protection inside of the Windows kernel, which is heavily obfuscated. I don't really know what the other functions do, but at least seeing the first functions might be interesting enough. Then, let's talk about one other metric, probably the easiest one, which is known as frequently called functions. The idea behind is that if we have a lot of different code locations, which all call the same function, we might want to probably take a look at this function. So, what's basically question here, what kind of functions are typically called? Well, the most promising here are API functions. So especially in the context of embedded or statically linked executables, this is a great approach which allows you to identify API functions. Of course, you don't find all API functions with that. And of course, you don't have the guarantee that each function of them is an API function. However, it helps you for sure to find the most common API functions, something like string compare, malloc, free, and so on. And sometimes it can even detect string decryption routines and hash functions in malware. So the most frequently called API functions are related to memory management, like alloc, free, malloc, and so on, data movement, like memcopy, string operations in all kinds, like string lang, string compare, string copy, and so on, and then, of course, also file parsing, file I/O operations, like fopen, fclose, fseek, and stuff like that. So let's take an example at some Linux malware, which belongs to the XDOS, X or DDoS family. This is a statically linked library. However, the good thing for this case is they had symbols enabled, which makes it quite easy to verify the ground truth. And as we can see, nearly all of the functions here we see belong to library functions. So the most frequently called functions are for sure library functions here. If we take another example, some plugx malware, the results don't look that good. So we see most of the functions are not good. However, the most promising ones, they are really important. They are used basically as CSC32-bit, CSC32, and load library A. These functions basically implement the hash-based import hiding, where they use CSC32-bit as a hash function, and once they check the hash, the computed hash, against the constant, and it matches, they start calling load library A and importing the import. And there's one more thing I would like to note here. You see, these are the only one which are very often called frequently. And we see that they have exactly the same number of calls. So this gives us a good indication, alone by looking at the numbers, that they might be similar to each other or used in a similar context, which might also be a good indicator. So now we had about complex functions with complex graphs, large basic blocks, and frequently called functions. Let us go into some more advanced stuff, like the identification of state machines. So the idea is to detect code constructs which look like that. So basically, a complex loop-based dispatching routine, which can be realized. Yeah, we are looking for loop-based dispatching routines, which often are realized as a switch state statement, where we have a while true loop, which then dispatches a state. So typically, these state machines implement a complex program logic. So there are just some examples what it might be, like file format parsing, or input validation and sanitization, network protocol dispatching, where you always wait for new commands from the server and start dispatching it. In this context, even CNC server communication, or also data encoding and decoding. So how this heuristic work is basically that we distinguish between a controller and controlled blocks. The controller is this basic block on top of here, which controls the loop. It is a single loop entry, and it dispatches the control flow to the individual blocks. These blocks, these controlled blocks, are states of the state machine. And what we can compute is that if we identify a state machine in the function, we can compute the number of controlled blocks relative to all the blocks in the function. The larger this number is, the more states this function has. And this is something which works also quite well. So there are only some examples which is depicted. So in the same plugx malware sample as before, we can find the CNC communication and command dispatching. If we take ls from core utils, which basically lists directories, we'll find the state machine, which corresponds to the recursive directory traversal. If we look into GCC, we find the file parsing and tokenizing logic. So now let us talk about the last heuristic, which is known as uncommon instruction sequences. So the idea is to find instruction sequences which are really uncommon, like this one. This one is an example from VM Protect. So there's an observation how we can detect something like that. So the observation is that a statistical analysis of assembly code is quite feasible, and that this allows us to predict the structure of code. On the other hand, if we can predict the structure of code, we can also find code which we can't predict the structure for, and this one is uncommon code. So let me give you an example. This is just one random function of some random binary. And this function has a lot of patterns which are quite common. So what's so common in this function? Well, for instance, the instruction sequences push, move, push, or pop, pop, return. This is quite common because this is the typical pattern for function prologues and epilogues, which happen in most of the functions in a binary. There are other patterns, like move, move, call, where you do some data movement and prepare a function call by moving the parameters and then performing the call. So this is also a quite common pattern. And last but not least, data movement, like lia, move, move, or move, 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 and so on and so on. So, and now our goal is to use this to build something based on that, such that we can find unusual instruction sequences. So this typically means that we can detect a wide usage of floating point instructions. We can really efficiently pinpoint with that cryptographic implementations, and furthermore, of course, all kinds of obfuscated code. So how does this work? It's a two-step approach. In the first step, we build a good ground truth about the 1K most common instruction sequences. So what we do there is we build a large database and throw in all kind of normal code, like core utils, system32, the folder, then we put in some compilers there, something like Blender, some multimedia player. So we take a large code base and put it in there. And then we count all instruction sequences over all binaries. And then we just take the 1K most common ones. For x86, this is, for instance, move, move, move as the most common one, then move, call, move as the second most common one, and so on and so on. So once we have a ground truth like that, we can use this ground truth to find uncommon sequences. What we basically do is we ask how many instruction sequences in a function are not part in the ground truth. In other words, the more sequences in a function are not represented in the ground truth, the more it distinguishes it from normal code or from common code. And this way, we get a relative good indicator about strange behavior. However, this is the only approach until now which looks at the code itself. So remember, we were talking about doing it in an architecture-agnostic way. So what can we do here? Well, instead of doing it in assembly code, we can use an intermediate representation for that. For instance, Ghidra's P code or Binary Ninja's low-level IL. So, and if we take a look at the Windows kernel module there, which CIDLL, which is responsible for the authentication, we find that most of the functions inside there are related to cryptography, to symmetric cryptography. And there's one other function. You already see this in the function name, that it looks kind of strange. Well, this is one part of many hundred functions inside this binary, which implement virtualization-based obfuscation. So, in other words, with a lot of different metrics, like large basic blocks, complex control flow graphs, most frequently called API functions, common instruction sequences, and so on, we were able to pinpoint a wide variety of code, like state machines, cryptographic code, obfuscated code, network dispatching routines, and so on and so on. And yeah, the takeaways are that these heuristics are very efficient to implement and also can be realized in an architecture agnostic way. And it can be easily implemented on the disassembler of your choice. That they allow to detect a wide range of interesting code constructs. And of course, that false positives will occur. As said, these metrics are not meant to that they solve all your problems. Of course, they don't. But still, for me, I found them very useful in daily life, no matter what binary I'm looking at, to get some manual guidance where I should look first. So if you want to play around with that, I personally implemented everything some years ago on Binary Ninja. There is a Binary Ninja plugin. It works like that once you open a binary, you can go into the plugins folder and then select obfuscation detection, and then you can select the individual instruction, the individual metrics. And once you selected one of the metrics, you get in the log window basically a sorted list with scores where you can then take a look and click on the functions you're interested in and navigate that. So if you're interested with that, feel free to look at the code. You can also install it directly using the plugin manager. It should only take 10 seconds to install that. And then you can go. And otherwise, I would like to thank you for your attention. If you are interested in that, feel free to check out the links. Also, there's a reference slide where I wrote some blog posts about that, if you're interested in that. And otherwise, I'm now open for questions. Thanks a lot.
Have you tried doing any heuristic detections with constants? For example, oftentimes if you see an XOR with a constant, it's a really good indicator that it's a decryption routine, although it has a lot of false positives.
I didn't play around with that, but I think this would be pretty easy. So basically, it should be easy to check if there's a loop inside the graph. This is pretty easy. And then you can check inside the loop if there's an XOR with a constant. So yeah, I didn't try that, but I think it will be quite effective and shouldn't be also take that much time to implement.
Yeah, I was just wondering with your uncommon instruction sequences, it kind of looked like you were breaking things down into, is it usually broken down into threes? Or was it broken down to other like longer segments? Did you get like better results breaking things down by like trigrams or anything, or?
Is a function if it works on over all sections? Or?
Yeah.
Yeah, it works over all sections. It basically works over everything which Binary Ninja recognized as code, no matter the section. Okay, thanks a lot then.